Today we're going to start Unit 5, Differential Calculus. We're going to begin with Chapter 13, and Section 1 deals with limits of functions. All this material you have seen before in AP Calc last year, but it's worth going over and reviewing with you. We'll start with a definition. If a function f of x becomes arbitrarily close to a unique finite number L as x approaches c from either side, then we say the limit of f of x as x approaches c is L. In the notation, we write LIM with the subscript x arrow c, and then the function f of x equals L. So the way we read these statements is the limit as x approaches c of f of x equals L. When a function f of x becomes arbitrarily close to a finite number L, we say that that function f of x converges to L. Now let's look at asymptotes. The line y equals c is a horizontal asymptote of the graph of a function y equal f of x if either the limit as x approaches infinity of f of x equals c, or the limit as x approaches negative infinity of f of x equals c. The line x equals c is a vertical asymptote of the graph of a function y equal f of x if either the limit as x approaches c of f of x equals positive or negative infinity. So let's look at some examples. One of the most famous limits is the limit as x approaches 0 of sine of x over x. Let's look at the calculator very quickly and use that to find what this limit seems to be. So I'm going to graph y equal sine of x over x. Let me set my window from x going negative 2 to 2, scale of 1, y going negative 1 to 2 with a scale of 1. And remember, we're interested as x approaches 0 for this. Now, more about this later, but right now make sure that we're in radian mode. So here's a graph y equals sine of x over x. Obviously, at 0, this function's not defined. But as we get closer and closer and closer to 0, it seems like we are approaching a certain value. As we approach from the left, let's say negative 0.5, and then negative 0.2, negative 0.1. Looking at the y values, negative 0.01, it seems like we're getting closer and closer to the y value of 1. And similarly, from the other side, as we approach 0 from the right, let's say positive 0.5, and then positive 0.2, positive 0.1, it seems like our y values also are approaching the value of 1. So there's a hole in this graph at 1, but remember, for a limit, it doesn't matter what actually happens at that x value. We just care what happens as we're getting closer and closer to that x value from both sides. All right. Likewise, we can take our calculator and graph cosine of x minus 1 all over x and look at the limit of that as x approaches 0. And we'll find that that will equal 0. The first thing you always try and do with limits is plug in the value directly. But in both cases, that's not going to help us. If I plug in 0 for x, I'm going to get cosine of 0, which is 1, minus 1 over 0, which gives me 0 over 0, which is an indeterminate form. So we're going to have to use other methods. One method is using a graphing calculator and look at the graph. we like to also use algebraic manipulations when possible. Let's look at another limit. This time we're going as n approaches infinity of 1/2 to the n power. So just using some common sense, you can think what happens as we keep taking more and more products multiplying by 1/2. And as you can understand, our fractions, our answers are getting smaller and smaller and smaller. 1/2, 1/4, 1/8, 1/16, etc. So those values are getting closer and closer to 0. How about the limit as x approaches 0 of 1/x²? It might help to remember what the graph of 1/x² looks like. So in this case, as x is approaching 0, our graph is approaching positive infinity from the left and from the right. And since infinity is not a number, a finite number, we would say that this limit does not exist. But I'm not satisfied with that answer because we can be a little more explicit as to what we mean by does not exist. And so in this case, since from the left and from the right, it's approaching positive infinity, I would like you to write the limit is equal to positive infinity. Now that's not going to work in this next case. How about the limit as x approaches 0 of 1/x? Well, let's look at that graph. Now, as we approach 0 from the right, we're approaching positive infinity. But as we approach 0 from the left, we're approaching negative infinity. So the best we can do here is just say that the overall limit does not exist. We can't be any more specific than that in terms of the limit as x approaches 0 of 1/x. Okay, how about something that looks like this? We studied last year some rules about limits, and actually even in pre-calc, about when we have a rational expression of a polynomial over a polynomial, and we're taking x as it goes to infinity. So the rule was we look at the highest degree term in the numerator and the highest degree term in the denominator. If those two degrees are the same, then the limit as x approaches infinity is going to be the ratio of the leading coefficients. So the answer here is 3/2. This one should look familiar. Well, let me back up for a second. And by the way, if the degrees are not the same, if the degree is higher on top, let's say, for example, it was an x³ on top and an x² on the bottom. If the degree is higher on top, then the limit is going to be approaching positive or negative infinity. If the degree on the bottom is higher, then the limit is going to be approaching 0. Okay, so now let's look at this familiar form. What's the limit as h approaches 0? Well, the first question is, could we just plug in 0 for h? And when you do that, you'll see that you're going to wind up with 0/0, so that doesn't help. So maybe we should go ahead and expand this out and see what we got. So we're going to get the limit as h approaches 0 of x² plus 2xh plus h² minus 6. Be careful here, make sure you distribute the minus sign. Minus x² plus 6 all over h. We can see now that several terms are going to cancel in the numerator, and also that we can factor in h out of the numerator. And we're going to get 2x plus h all over h. And that certainly is not red. The h's will cancel. And so now we have the limit as h approaches 0 of 2x plus h. Now we can plug in 0 for h directly, and we're going to get a final answer of 2x. So the limit of that expression boils down to just equaling 2x. Here's one that sometimes confuses students. What's the limit as p approaches 2 of x squared minus 4px plus 3p? Notice we have two variables here. We're looking at the limit as p approaches 2. So you can think of x as a constant. So the x squared stays x squared. We're going to plug a 2 in for the p here and also here. So this winds up giving us x squared minus 8x plus 6. So be very careful and pay attention to what variable we're using in our limits and also what we're approaching. Okay, so now we have one that looks pretty complicated. First thing we try, can we plug in 0? And when we do, we wind up getting 0 over 0. So that's no help to us. Can we manipulate this algebraically? Well, that's a little tricky. At first glance, you might think, no, there's not much we can do with this. So we're going to have to be a little creative. And quite often when you see something like this, especially with radicals, think of multiplying by a form of 1. That's not changing our expression, but by multiplying by the conjugate, something nice is going to happen here, because some things are going to cancel. So let's see what we get. On the top, this is really going to give us the difference of two squares. We're going to get the first term squared, which will cancel out the square root. So we'll get x squared plus 4. And then minus the second term squared, which is just 4. In the denominator, let's leave it factored. In the numerator, the 4's cancel. And then we have x squared over x squared, which will cancel, and that'll become 1. And so now we're left with the limit as x approaches 0 of 1 over the square root of x squared plus 4 plus 2. Now I can plug in 0 directly for the x, and I'm going to get 1 over the square root of 4, which is 2, plus 2, which is 4. If you wanted to, you could have graphed this function and then looked at the graph as x approaches 0. But you should be able to manipulate this algebraically without using a calculator as well. But you can check that even with a calculator, you'll see that it is approaching 0.25. Lastly, there's some properties of limits that you have seen before. It comes on page 576 in your book. I've made a copy of them here. You can refer back to the page in your book as well. And these are properties you should know, that the limit as x approaches a of a constant b just equals b. If we're taking the limit as x approaches a of a constant times a function, it's going to equal that constant times the limit of the function. Also, the limit of the sum or difference of two functions will be the sum or difference of their individual limits. The limit of a product of two functions will be the product of their individual limits. And the limit of a quotient of two functions will be the quotient of their individual limits as long as the limit of the denominator, the function in the denominator, is not 0.